Hello and good day everyone, my name is Ron and let us answer some separation processes problems. So this is a problem inspired from problem 26.8-4 of Transport Processes and Separation Processes Principles, 5th edition book by Jean Copley's, Hercel, and Lepek. So the problem is a modified version of the problem reference, and this is what it says. The following feed of 7,500 moles per hour at 40 degrees Celsius and 500 kilopascals pressure is fed to a fractionating tower, where the components of the feed is N-pentane at 0.73 mole fraction and N-hexane at 0.27 mole fraction. This feed is distilled so that 96% of the N-pentane and 4% of the N-hexane is recovered in the distillate, all while 94% of the N-hexane and 6% of the N-pentane is in the bottoms. So using Raoult's law, find the minimum number of theoretical stages. So this is the given diagram in the given of the respective problem. So as you can see, the feed and the outlet properties. The light key is the pentane, since it is the majority according to the problem, and the distillate, and pentane is the majority, so that means it's the light key, and the heavy key is the majority of the bottoms, which is the hexane. Okay, then the required is the minimum number of theoretical stages, and we need to use the following. So I'll specify the assumptions later. For the simulation procedure, all we need to know is these following values and its uses. Raoult's law. Raoult's law. Okay. So to start, let us go to DWSim and create a new process model and specify the following parameters. So we'll wait for it to load. So we'll click next, and what are the different parameters here? N-pentane, so N-pentane, and another is N-hexane, normal hexane. Alright, that's it. The property package to be used is Raoult's law, so we'll find here Raoult's law, add it. Next, system of units. We'll try to make our own customizable system of units. So from the diagram, the mass flow is at moles per hour. Moles per hour. Then pressure is kilopascal. Then the temperature is at Celsius. Then Celsius, kilopascal, and mole per hour. Celsius, kilopascal, mole per hour, and that's it. That's the notable units that we need to define. Afterwards, so we can just use a shortcut column or this shortcut distillation column. So we go a shortcut column, and automatically these streams would be automatically provided. Then we just need to rename it as follows. So this is the inlet stream. So we'll go here as inlet, and the third here is the distillate, and this one is the bottoms. And let's specify our variables. So the inlet stream, it says here 40C, 40 degrees Celsius, and it's 500 kilopascal. Then the compound is that mass flow, however, it's in moles per hour. So we'll put here a molar flow of 7,500 moles per hour. Then the compound amounts for the A is pentane, 0.73. So pentane is 0.73 and hexane is 0.27. Double check if it's correct. If it totals to 1, it is correct mathematically. So mole fraction 0.73 and 0.27. Next, we'll now go to the column itself. So the column, the inlet is connected, distillate and bottoms, the condenser duty, reboiler duty. So the light key is pentane, the heavy key is hexane, the light key mole fraction in bottom. So as you can see here, according to the problem, in the bottoms, all while in the bottoms part, the light key is pentane. And then the light key mole fraction in the bottoms is 6% or 0.06. Then the heavy key mole fraction in the distillate. So heavy key mole fraction in the distillate, heavy key is hexane, and this in the distillate it is 4% or 0.04. And there's no specification about the reflux ratio, so we'll put it as normal, 1.5. Then the condenser type is total, condenser pressure, the boiler, and this is the result. So according to DWSIM, the minimum number of stages is 5.1766. So that's the answer in terms of DWSIM, 5.1766. But how do we know if this answer is actually logical? Therefore, we need to calculate this using hand calculation. So the following details are what I did to prove that the answer in DWSIM is actually very accurate or very precise. So I assume the following in order to make sense of the solution that is to come. I assume that it is under constant molal overflow, meaning that the enthalpy of vaporization is equal to the enthalpy of condensation. It's constant relative volatility. So it has the average relative volatility is equal to the relative volatility of light key and heavy key. And the column is operating at total reflux. And of course, it obeys Raoult's law. So how do we solve this using hand calculations? So we'll need to do a pre-solution. If you have solutions thermodynamics under your belt, you might feel familiar with this equation. So this is an equilibrium relation of pentane using Raoult's law. Pentane at gas phase and pentane at liquid phase. This is the fugacity coefficients, activity coefficient, and fugacity coefficient. So the fugacity coefficient, is 1 when assuming Raoult's law, and pressure is the total pressure. And the activity coefficient for liquid is 1 for Raoult's law, and the fugacity coefficient is at saturation pressure at A. So manipulating, we have a relationship, and in terms of hexane, it's the same procedure. So this is the relationship. Then we need to find the relative volatility of binary mixtures. So this relative volatility has the form of Ka over Kb. Ka is simply the ratio between the gas mole fraction and the liquid mole fraction of one component. And knowing that, this is their ratio. And since we know that this obeys Raoult's law, this means that this one is applicable to this equation. So substituting, since we already have the ratio, if we can just put this under here, this is its equation, and we'll just put them under, we'll just substitute them, and we get that the overall relative volatility of binary mixtures is the saturation pressure of A over the saturation pressure of B. How do we find the saturation pressure of A? We can just use Antoine's equation of correlation. This equation is very well known, and its values, I use the values given from the SVA or Smith Van Ness Abbott and Swihart Handbook of Introduction to CHE Thermodynamics 8th edition. Using that, I found out that the saturation pressure of pentane is this value, 115 kilopascals, and the saturation pressure of hexane is 37.31 kilopascals. Then, finding the relative volatility using these values I calculated earlier in the derived equation, I found out that the relative volatility of binary mixtures is 3.1069. We'll set it aside for later. We'll set this aside as we now go to the analytical equation. So, how do we find the minimum number of stages using hand calculations? There is a graphical and analytical method. So rather than doing graphical, which will take a lot of time since there's a lot of conditions we need to satisfy, using an analytical equation just uses one analytical method just uses one equation to solve the entire problem all at once. And this equation is what we know as the Fensky equation. There are also other types of shortcut equations for distillation columns, such as the Underwood equation and the Gilliland equation. But in order to find just the minimum number of theoretical stages, we can just use the Fensky equation. The Fensky equation is as follows. So this is the mole fraction of the light key at distillate, mole fraction of the light key at bottoms, and the average relative volatility. So since we assume this is actually the this is incomplete, but since we assume that this one, the relative volatility, so let me delete this since I already explained earlier. Since we already assume that this one, relative volatility, is at constant, that means its average is equal to the relative volatility calculated. Therefore, we can just substitute this value into this value. So, doing that, substituting everything, noting that at the distillate is 0.05. The mole fraction of the distillate of pentane is 0.96, and at hexane, and the pentane is 0.06. So, apologies. This is supposed to be 0.06, so let me recalculate it live. So, 0.96 log of 0.96 over 1 minus 0.96 times 1 minus 0.06 over 0.06. Then over the log of what we calculated earlier as the average volatility, which is 3.1069, is actually a value of 5.2306 theoretical stages, or we can just approximate it to 6 theoretical stages. Quite nice. So in comparison, so how would we compare this hand calculated value to the DWSIM value? Well, remember what we calculated, the minimum stages is 5.2306, then the simulated value is 5.1766. Finding its percent difference is equal to, using this formula, is equal to 1.04% difference. This means that what we calculated and what the simulator gave are very close in values, which concludes that what we done hand calculation wise and what it simulated is logical and correct in manner. So overall, the simulation and the hand calculations are very close. Thereby, I conclude that in order to fully solve this problem, the minimum number of theoretical stages for this separation to occur is at around 6 theoretical stages. So again, why 6? It's because from our calculated is 5.2306 and from our simulated is 5.1766. However, we're talking about trace. There is no tray that is in a fraction form. There's only trace in whole number form. And since it goes past the number of 5, we equated another additional tray. So that means that regardless if we have these different decimal values, approximated it into upper, rounding it up further, it will be both at 6 theoretical stages. So to solve this problem, to initiate this separation, it requires a minimum number of 6 theoretical stages in distillation. That is all. My name is Ron. Thank you and good day.